Okay, it's 5 p.m., ladies and gentlemen. Monday, 5 p.m. means that we have our next exciting presentation on sustainability in computer science. I'm very much happy and honored that this time we have Nysret Musliu. Nysret is really one of our kind of spearheading researcher in the area of logic-based AI optimization and scheduling. He has a Christian Doppler laboratory in this area. And I was particularly pleased when I have learned that he's using his technology also in the area of kind of computational sustainability. And I guess this is something what we will hear about today from Nysret. I also want to mention that Nysret, next to his Christian Doppler laboratory, he's working also in the cluster of excellence bilateral AI, and most probably he's the forthcoming chair-head of the Center for AI and ML at TU Wien. So Nysret, great to have you, and it's your floor.
Okay, thank you very much for the introduction. So yeah, my today's presentation is about AI methods and also optimization, but also the hybridization for different kind of applications. And mainly I will show here our work that we did in the Christian Doppler Laboratory for AI and optimization for planning and scheduling. This laboratory is running already 7 years, but we have also some works here which were supported by FWF, FFG, and so on. So I will start with some applications, and those applications are from different areas: employee planning and scheduling, production planning and scheduling, and also I will say something about one FFG project which deals with food waste reduction. And then I will give an overview of methods which are used to solve this kind of problems. And especially, I will talk something about modeling different kind of methods like exact, heuristic, and hybrid techniques, and also talk about some methods which we have been developing recently based on machine learning, and especially in reinforcement learning. And to the end, I will give some conclusions. So those are the applications which were investigated in our laboratory until now, not only in our laboratory, but also, like I said, in other projects, FWF, FFG, and so on. And as you can see here, we have different kind of real-life applications, starting from employee scheduling problems like nurse rostering, break scheduling, rotating workforce scheduling, and so on. Timetabling problems in schools like high school timetabling, production scheduling problems like parallel machine scheduling, industrial oven scheduling, and so on. And there are a lot of other problems you see in the second column, and I will talk for some of those problems. So why this lecture is about sustainability, and why we say that we have also some impact in this area, because most of those problems have some connection to the sustainability goals of United Nations, and especially to goal number 3 about well-being of employees and so on. Then goal number 12 about responsible consumption and production, and so on. So there are at least 2-3 sustainability goals which are connected to those applications which we have in this presentation. So let's start with the first one. This is about employee scheduling, which it's a very interesting problems. It looks to be a very simple problem in the first moment, because most of people think that those kind of schedules can be just done manually, and there is no need really for computational methods. But yeah, our experience showed something else, and actually obtaining or generating good employee schedules, which are very good for employees and also for companies, it's a very hard problem. And why we want good schedules for employees is because they influence life of employees. It's very important to have good schedules. In some branches, of course, not so important, but especially if you work 20 if in 3 shifts and so on, this is very important to have a good sequences of shifts. And because they can have, of course, some impact on health of employees, social life, and motivation, their motivation at work. And of course, in general, the organizations and public sector want to meet their requirements because they also need to assure the quality of their services and the operations. So those kind of problems appear in different companies. And as you can see here, for example, we have applications in airport, call centers, air traffic control, hospitals, public transportation, production plants, and so on. And why we need or why it's hard to generate such kind of good plans is because we need to take requirements from different stakeholders like employees. We have a labor law with different rules about about the schedules, and of course we have companies who have their interests and want to fulfill their requirements. So let's see a typical case of workforce scheduling or employee scheduling in general. So in general, in every organization, usually you have some requirements which are given and you need to fulfill. For example, we see from the curve here, from this red curve here, that we need on some day from 5 to 6 no employees, but after that we need 5 employees and then 6 from 8 to 11 and so on. And this may change, of course, depending from the organizations. And in some organizations like airport and so on, this fluctuates. The workforce requirements change really during the time. And it's very hard to generate the shifts and also breaks in this case so that you fulfill all those requirements. So if you see these red curves, which are the requirements, we see here some shifts we generated. For example, shift A here, which starts at 8 o'clock and ends at around I don't see it exactly here, but around 13, I think, and so on. And in between, you see this white spaces here, which are called breaks. So you may we may assume that breaks are not very hard to be generated, and generally in general this is true, but especially in areas where you have many breaks, for example, in air traffic control and so on, you may have up to 10 breaks during the shifts because the employee must have a regulated break so that they are concentrated all the time. So in those cases, you really need to generate good schedules with shifts and with the breaks inside, which fulfill a lot of requirements. So after you have those kind of shifts, then you can assign them to particular employees, and this part is called rostering. And here, for example, we see employee A who works on Monday in this F shifts, so in German, Frühschicht or morning shift, and then on Thursday and Friday it will work in afternoon shift and so on. And you have a lot of constraints about this schedules here, and I will present one of the problems with different constraints. It's one of the simplest problems in employee scheduling, but it's also hard to solve if you want to especially fulfill different kind of soft constraints. So here, for example, we see a typical schedule for, in this case, 12 employees during 1 week, and we see the shifts there. That means we have given some shifts which have to be assigned. We have given number of employees, so we already know how many employees do we need. And we want to generate a schedule which fulfills different kind of criteria. Of course, one of the criteria which is very important here are the temporal requirements. For example, every hospital needs a number of nurses or doctors in a particular day or shift. And here we can see, for example, that for night shift, we need exactly 3 employees on Monday and so on. Then we have not allowed sequences of shifts, for example, night, free day, or night day, and so on. Those kind of sequences were proposed by researchers based on different studies and where they studied how much impact those sequences have on the health of employees and also in the sleep and so on. And then, of course, we have some constraints regarding the maximum and minimum length of periods of successive shifts and working days, day of blocks, and so on. And you can add here also a lot of so-called soft constraints. So the constraints you see here are hard constraints because they must be fulfilled. So you should not have a schedule which contains some sequences which is not allowed. But you may add constraints which it will be good to fulfill, but maybe they are not always fulfilled, and they are called soft constraints. For example, optimization of free weekends may be one of the soft constraints. And recently we had problems where we have many more soft constraints in some of the papers, and finding those schedules which are where you have multi-objectives, it's even harder than just finding one schedule with the hard constraints. So other problems which we had in planning and scheduling and the project scheduling also appeared in different areas of the industry. And what is important for those applications is that regarding the sustainability, if you manage to find good solutions, you may reduce the resource consumption, including the energy, of course. And of course, you also increase the production efficiency. But in general, every time you generate schedules in production and so on, this may be very important for resource consumption. And of course, this is an important goal. So we see here three problems. One of them comes from the test laboratory scheduling. Another one comes from the semiconductor industry, oven scheduling domain. And another one is from the industry which produce or color different parts of the cars. So let me just say a few words about this test laboratory scheduling and why you can reduce the resources, in this case, resource consumption. So for this problem, so we worked with a big company which basically makes tests for different parts of the cars, especially tests regarding the electromagnetic compatibility. And for those kind of tests, you have special rooms, special equipments, you have employees which have different qualifications and so on. And usually you get a lot of tests you have to do, and they are grouped in so-called jobs. So you need to group them in jobs, and every project has different jobs which need to be scheduled somewhere. So the idea here is to, this problem is also called project scheduling problems. It appears also in other areas, of course, as a project scheduling problem, is to assign those tasks or jobs to a particular time points such that you have enough resources for those jobs. And as you can see here, different resources like equipment or workbenches and so on are needed for those cases. And of course, you come in conflicts here because you have limited resources. And what you want here is by better grouping the jobs and better assigning them to finish earlier the projects and reduce the resource consumption. Like I said, another problem, which is called oven scheduling problem, we solved this problem recently with the PhDs and postdocs here. And in this problem, which appeared in the semiconductor industry, you need so you have those ovens and you have some jobs. You need to put those jobs in the ovens. And what you want is to make a good grouping of the jobs so that you can use the same oven for as many jobs as possible. And by doing in the right way, using those ovens in the right way, you can reduce a lot the energy on those cases. And there are many constraints and solutions which and objectives which are needed here for this problem. I'm not going to explain those here, but yeah, I also put it here, the papers which you can read if you're interested in these problems. And there are many other problems, like, for example, torpedo scheduling problem in steel industry, parallel machine scheduling problems, classical ones which appear in different areas, paint shop scheduling problem, and so on. So I hope I convinced you know that we have different problems which are important in the industry where you can really where you need good solutions they are often, unfortunately, still obtained manually. So usually there are often a manual expert who are, of course, who are expert in this area and can do pretty good schedules. Of course, not the optimal ones, but you need additional employees for this kind of task. And like I said, you may lose also very good solutions in those areas. So now, why do we need solutions for this or methods, new methods for this kind of problems? Um, the problems which I showed before, all of them belong to the class of problems which we call NP-hard problems, and every student of computer science know what NP-hard problems. But basically, those kind of problems are the problems where we don't know if we have algorithms which are efficient and can run in polynomial time. And in the opposite, we have the problems which can be solved in polynomial time. For example, if you take the sorting problem, this is a easier problem to be solved because we have their algorithms which work in polynomial time. But for solving NP-hard problems, actually, these problems those problems we still don't have methods which can solve every NP-hard problem efficiently. Of course, you can solve some of them if they have a special structure, but we are forced here, of course, to use different methods, and sometimes we even cannot reach the optimum because, as you see here, if we just take, for example, this rotating Wilford scattering problem, the number of possible candidate solutions is huge, and trying all of them exhaustively is not possible in most of the real cases we have. Okay, and maybe just to show another application before I go to the methods is this food waste reduction. So this is the project, and actually the methods which are used here are a bit different from the methods we use for optimization problems. For this project, we are with several partners here in Austria, as you see, like Fraunhofer, WU Wien, and then Kastner, Metro, Spar, ITPS, and Invenium, which are some software companies. And the idea here is that we are motivated by the current waste of the food in supermarkets and so on, and want to develop and see how the machine learning methods can help to reduce this waste. Of course, in the industry, there are already supermarket and so on are already using such kind of prediction methods, but using new data and using new methods and so on can help them to develop new methods. We are not developing here products for them because this is not a contractual project, but we are analyzing in large scale with different data sets and so on how can we improve the solutions in these areas. So we are working in two directions here, and I have here at TU Vienna a PhD student who is working in this topic, and he is especially looking on more advanced forecasting methods. For example, we are also trying NoX, LSTMs, and so on. Also what he did is to get different new features for the data sets we are using there. And in the literature, a lot of features have been used for this kind of problems, like also weather features and so on. But we have also new features about the mobility and also new contextual data in general. So there are different input data we take, of course, normal data about the products, sales data, weather data, movement data, conceptual data, and so on. And those are, of course, all of them important to be able to make predictions. So we are almost in the last year of this project, and the data have been collected, and we have created a lot of data sets for different products. We also incorporate different data from weather, movement data, and so on. And we also have new features there. there was a lot of work of the PhD student in data preprocessing and so on, but this process also has been finalized. And we have also a large-scale evaluation in different products and analyze the performance across different data sets. And this gives to us several interesting insights where it works better and where it doesn't work better. So current work, there's a platform implementation, not only from our side, but also from the other partners. And this platform will be also used by the other partners to see if they, in their data, can improve the results in general. So we hope that with the end of the project, we'll have better results than the solutions which are currently used in these organizations. So now I can start now with some methods which are used in general about the optimization problems which I mentioned before. And the focus here will be in AI and optimization techniques. So the way we are dealing with the problems which we have from the industry, especially in the CD laboratory, is in these three stages you see here. So of course we may have sometimes existing problems which have been already introduced in the literature, and then we go directly to develop new methods, which of course have not been developed in the literature yet. But often it's really interesting that, like I said before, some problems are solved manually. We see in the different organization. So we have to formulate, and we see that there are different problems. We talk to the industry, and then in this phase here, we make formal mathematical formulation. Of course, we have a look if there are related problems in literature. Sometimes, and actually in this CD lab, we introduced a few new problems in the literature which were not described before mathematically. But we also have to do here complexity analysis, because sometimes it can be that the problem is easily solvable. So, but usually we have NP hardness for this kind of problems. We analyze also general variance of problems, of course, for basic research. And what we try, and we try it all the time, is to provide also new instances to the literature. So sometimes, of course, we cannot provide all the real life instances, but usually we also try to generate our own instances which are which mimic the real life instances. And this is also interesting contribution in general, because if other researchers want to compare, they can have a benchmarks to compare on those instances. And regarding solving those problems, so there are usually different stages. So one of the first stages, which is usually tried by researchers, is modeling of those problems. So we have already the formal mathematical formulations, but on the other side, we have different solvers, which are based in mathematical optimization or AI and so on. And they work good or bad, depending from that, how do you model the problem? And there exist different ways to do this modeling, and this is not an easy task. Okay, so it looks to be a very simple task, but often you need to think a lot for a good modeling of particular problem. And then techniques which are used a lot are, of course, AI and optimization solving techniques on those solvers. So you don't need to implement them. Usually you can use them based on the modeling which you have, but usually it doesn't work very well for large problems. So those solvers may be able to solve some large problems, but you can reach the point usually in practice that you don't get from those solvers directly a solution. So that's why still research in this area is needed, especially in direction of hybrid algorithms. And what we also did a lot is algorithm selection and instance space analysis. So we divide the methods which solve this kind of optimization problems in different parts. So first, we have so-called complete methods. What we mean with complete methods is that those methods will guarantee to find the optimality if they have enough time. And usually this is not the case, but they are, of course, very useful because one can test for small examples and also mid examples often, sometimes also for large examples, depending from the problem, if you can solve the problem to the optimality. Of course, you don't need always optimal solutions, but this is, of course, and in practice, usually the practitioners are also satisfied with some approximate solutions. But we are, as researchers, of course, we want complete methods when possible. Um, Often we are forced to go to heuristic techniques because we cannot solve the problems with the exact methods or complete approaches. And there exist plenty of heuristic techniques like taboo search, simulate nailing, mimetic algorithms, evolutionary strategies, and so on, which are basically frameworks of meta-heuristics how to solve those problems. Still here, if you want to solve the problem, is not so simple, just implementation of some techniques, but you have to think a lot of the neighborhoods and to do a right configuration of the algorithms. And especially the operators you use inside of those algorithms are important in those cases. What nowadays is very popular, and actually where we have nowadays the most powerful methods is in these hybrid methods, where you try to join methods from different areas, and there is also a conference CPAIOR which tries to hybridize methods from AI, constraint programming, operation research, and so on. And there exist different approaches which are very robust approaches. One of them, for example, is large neighborhood search. Then you have hyperheuristics. I will say something later on about those methods. And what is now, of course, very popular are the machine learning-based approaches. In one side, machine learning-based approaches, which are used together with those kind of techniques which already exist. And a lot of people are also working now to this end-to-end solving with machine learning-based approaches. They are still not very good for optimization problems and cannot solve. So if you use LLMs and so on, not really scheduling problems, but there is a lot of research happening in this area currently. So if we want to model a problem, which is, like I said, not a simple task, we can use different solvers. And there exist solvers from big companies, mathematical programming solvers like from IBM, Cplex. Then you have Gurobi, it's also one of the best solvers. You have also open source solvers like Skip. Then we have constraint programming solvers, which are more from symbolic AI community. And there is a solver from Google called OR Tools, but also Shaft CPU optimizer from IBM and so on. And this OR Tools, for example, Google is one of the best CP solvers currently. It's also open source software, so people can use it and also change it if they want. And there is also this mini-zinc challenge. In our research, we are also using a lot this constraint language called mini-zinc, because if you model the problem there, you can solve with any kind of solvers you see here, because the problem model is translated to them. And this is a very good benchmarking for different kind of problems. Another area where the solvers now are also very good is in the answer set programming. Our institute is also working a lot in this area. And one of the best solvers like Potasco is from Potsdam, but DLV was also its development started here in our group, and it's maintained now from Calabria, and those kind of solvers are also able to solve pretty large problems and comparable also to constraint programming. And of course, SAT is also a community which has very good solvers nowadays. Some of the problems can be converted to SAT and also solved very efficiently there. Okay, maybe I'm not now going to give the models of our problems, but just to give an impression how this looks like. For example, if I take rotating for scheduling, the problem which I had before, a constraint model will look like this one here, which is, it's kind of mathematical definition of the problem, but what makes difference, for example, in constraint programming is that there exist so-called global constraints, which are more efficient implementation of those kind of algorithms. You need to look on symmetries and redundant constraints and so on to improve the solving process. Yeah, if you take mixed integer programming formulation from mathematical programming, for example, in machine learning, this will look like this one here. This is more near to the mathematical problem definition. But here also you need to think about different ways to model the problem. What is the variable? How do you present the constraints and so on? So there are different possibilities to do that. And yeah, there exists a lot of papers which deal with this different ways of modeling of the problems. Then we have local search techniques. So maybe just to give the main ideas of local search techniques. So those are incomplete techniques. That means we cannot guarantee the optimality. Even if we let run for a longer time, we may reach optimality, but we don't know if we have optimal solution, except we have some results for this kind of problems from other methods. But they're very interesting methods because they can pretty fast find good solutions for most of the problems, NP-hard problems, which are acceptable in practice. And what is the idea of local search techniques is basically that you start from some initial solution, the solution X here, and instead of looking on the complete search space here, you just look on the neighborhood of this solution. So you need this so-called neighborhood relations operators, which change the solution step by step. And then based on some strategies, you take the next solution in the neighborhood and then continue until you have a good solution. So the solution is iteratively changed, and you decide in every step to accept or not. And you may have some more sophisticated mechanisms too. So if one wants to implement a local search techniques, this is a simple process first because yeah, you need to construct the initial solution, but generating neighborhood, like I said, it's important to have the right operators. Then you select from neighborhood one of the best solutions usually, and then you repeat this process. This kind of techniques, which is the hill climbing techniques, usually will get stuck in local optima very fast. So that's why we need these more advanced meteorist techniques, which include some more complicated mechanism to escape the local optima. And among those techniques, which I think are the most powerful, are the simulated nailing, taboo search, and large neighborhood search, and especially large neighborhood search nowadays is one of the most powerful techniques in this area. Okay, what are the neighborhoods? So neighborhoods are like you see here, basic change of the solution. So in this case, for example, if I take initial solution, which looks like this one here in rotating over scheduling, I could just swap N and D here, and I may fulfill some of the constraints there. So local search or neighborhoods are based on the way that people also solve the problems. So usually if the human planner wants to make a schedule in the hospital, it will start maybe with some schedule and then try to swap the employees and so on. But for example, in this case, it's also important to swap more employees together, and you can use different kind of neighborhoods. If you have machine scheduling problems, you may change the jobs between different machines. If you have a route finding, you may swap. So there is this, for a traveling assessment problem, for example, one of the best known heuristics is based on the key opt move, which swaps different edges and so on. And of course, if you have more complicated problems, you may need more complicated neighbors. In the area of evolutionary computation, you have additional operators which are called crossover operators. So the idea here is if you have many solutions, then you try to also join two solutions and get a better part of one solution and another. And by joining two good parts, you may have a better solution in general. And in general, the evolutionary computation mimics this evolution from the nature. I think my personal opinion is that for combinatorial optimization, they are not so good like local search, but they are for different kind of problems also good, and especially memetic algorithms, which combine genetic algorithms and local search, are very good also in general. But only sometimes why GAs are not so good, maybe in some applications, because getting those crossover operators is very hard in some cases, if the problem is more complex. Okay, and then we have hybrid techniques. So in hybrid techniques, we try to join different areas together, methods from logics, from mathematical optimization, from AI, like machine learning, and so on. And those techniques are pretty powerful nowadays. So I will show a few works we did which use machine learning in these kind of applications. And one of them is the algorithm selection. So the idea here is that if you want to solve one optimization problem, but not only optimization problems, also if you have, for example, a data set in machine learning, and you want to know which algorithm will work best there, usually you don't know. I mean, sometimes as an expert, you may know based on some characteristics that this algorithm may work better or this one. But in general, it's hard to know this because of this no free lunch theorem, which basically says that there is no algorithms in those areas which outperforms all other algorithms in all possible instances. Because no matter if you have, for example, machine learning, deep learning, or whatever, you can construct examples where they will not work there. So that's why this question of how to select the best algorithm for a specific problem instance is very important, because in that case, you don't need, of course, to run then all the algorithms, and you also reduce running times and so on. And we have been working for several problems in algorithm selection. So maybe just to give an idea how algorithm selection works. This is based in this so-called RISE framework, which is presented in this slide, which was actually published already in 1976. So the algorithm selection was not really, not a new topic, but it existed, but it was not really used much. And in some time points, people also recognize that algorithm selection, machine learning, optimization, and so on is actually the same question. And this question can be anywhere else, anywhere where you have two methods or three methods, whatever, which perform differently in different instances. You may use this method selection or algorithm selection in general. So the idea in algorithm selection is based on generation of a lot of instances, which we call this problem space, and characterizing those instances with some features. So if you have features which characterize the instance, which are not only direct features like the size of the problem and so on, but more sophisticated features, and you train then the algorithms, different algorithms on those instances, then you can create a data set which tells you about the performance of each algorithm in each of the instance based on its features. And this is actually, and based, of course, some performance metrics you want to optimize. And this is, of course, nothing else as a machine learning problem. So if you have now a new instance, you can extract the features from this instance, and then you can ask your model, your machine learning model, which algorithm to use. In this case, is a classification problem. But it can be also a regression problem if you want to predict how long it will take for one particular algorithm. And there are a lot of applications you can use algorithm selection. We have been working especially for TSP, tree decomposition, and different timetabling problem. And we have several results, especially for the features there. Okay, so I already said this, but maybe just to give an impression how this looks like in a machine learning setting as a data set. So basically, for example, if I take the SAT problem and I want to know which algorithm should I use, I create first the data set, and I see that for 100 clauses and 80 variables and a lot of other features which are not presented here, algorithm 1 was performing best and so on. And then if I learn on this data set a classification model, then I can predict for this instance which would be the best algorithm without running all of that. And of course, this works not always perfectly. So you may not have accuracy of 100%, but still often you have very, very good results in this direction than just using the algorithm, which was the best in majority of the instances. And in the same way, you can use machine learning to predict the performance of the algorithms. For example, in this case, we have a regression problem. I let run the algorithm in different instances. I get the running times of the algorithm on those different instances. And then I can learn a regression model here, a machine learning model for predicting numeric values, which may be able to predict for the new instance how long it will take to solve with a particular algorithm. And the techniques you can use here are, of course, different kind of machine learning techniques like decision regression tree, random forest, neural networks, and so on. Like I said, this is similar to the process of automated machine learning, which also deals with this kind of things, but also in addition to the algorithm selection, also to the configuration of the algorithms. That means finding the right parameters for the algorithm so that you improve the or you have the best performance of your algorithms. And in general, the whole process in machine learning can also be done with these automated machine learning techniques, including feature selection, pre-processing, and so on. Of course, those methods sometimes may not reach the solutions human expert reaches, but you can save a lot of time if you use automated machine learning approaches. Another work we did in our lab is also the work in direction of instance-based analysis. So you can extend this framework of RISE, where you have different instances, but if you see that you don't have enough instances, you can try to generate new instances. And the instance-based analysis basically extends this. So this is the framework from Smith, Miles, and colleagues, such that you project the instances in two-dimensional space, and you can see where are the weaknesses and the strength of different kind of algorithms. And this is very powerful framework because you can, based on the features of the problem you have, and this projection, you can really see and analyze where are the regions of the instance space where your algorithm may not work, and based on this, or work good, and based on this, you make also the right algorithm selection. So what you see here, for example, is the instance space analysis we have been using for rotating for scheduling, where you see these instances which are called real here. So real instances, the blue ones, which appear somewhere in the industry. And then what we did, we generated a lot of instances, which are the green ones, so 2,000 instances to see the performance of different algorithms. And by using the instance space analysis, we saw that there is a huge gap between those two green regions here. And then we could generate additional 6,000 instances to really critically evaluate different algorithms in different kind of instances. And the instance space analysis can produce also these so-called footprints. And what you see here are, for example, different solvers, shaft one, shaft two, and meta-heuristic approaches. And you see the regions of the instance space where those algorithms perform better. And you can do by this also automatically algorithm selection. Another applications we had was in course timetabling. So you see here that we have 4 solvers, SAT, simulated nailing, hybrid, and ASP. And we have some instances which existed, real-life instances from different universities. And by instance space, we could generate a lot of other instances which are random ones, but which cover very well the space of the possible instances which can appear in this area. So it's a really interesting way to analyze the strength and weaknesses of different algorithms. And this is especially very important in general for research, but also in practice to use the right solutions for in different situations. Okay, and the last thing I want to show is the hyperheuristics. where we had some works on applying of reinforced learning approaches for hypereuristics. So the basic idea in reinforced learning is that you have an agent which has possibility to do different actions and different time points, and then you have environment which gives some rewards or penalties based on the action. And what you try here is to learn so-called policy in which you will know which action to take in which time step. So it's kind of algorithm selection, but actually for every time step, because you need to select one action for every time step. And this process of learning is, of course, more complicated than just classification in this case. And we have been developing hyperheuristic approaches based on reinforcement learning. So what are the hyperheuristic approaches? The idea here is that in general, we have often, if we want especially to produce heuristic methods, we generate the operators, and then we try to make a fine-tuned methods for this kind of problems. And in hyperheuristics, we want to have this domain barrier. So we want to have a method which is able to solve any kind of problems, a problem, but for this problem, we know maybe some small we call them operators or solution components which can be used. They have not to be very sophisticated, but they can be useful for solving the problem. And if you translate the hyperheuristic approach into this reinforcement learning, the agent will be in this case the hyperheuristic, the method you want to solve different kind of problems. The actions are the components you provide to this hyperheuristic. So the hyperheuristic doesn't know at all which problem it solves, but it just knows that it can use some operations to solve it. The problem domain is the environment. And what we did here is that we had some more sophisticated reinforcement learning, which use different kind of features about the state in which you are. Because if you can characterize the state very well with some features which are useful, then eventually you can learn also a better policy, which low-level heuristic or solution component to take in which time step. Okay, so now I'm not to the coming to the conclusions, yeah. So like I said before, many problems within sustainable applications are still solved manually. Also in big organizations and also in the Western countries, where I was surprised, there is a huge potential to improve such kind of solutions. There is, of course, also a good reason why companies often don't want to implement such solutions. So often it's not so easy to change the whole process, the company in which company works, and you need really a long-term project to manage to have these automated solutions. But we had several success stories for different kind of problems, and actually all those companies are very satisfied with the solutions we provide, also from the literature. And often, if you provide such solutions, you can also do better than human planners, or together with the human planners, reach much better solutions. In all those cases, or in many cases, this combination of AI and optimization techniques was crucial. So sometimes to reach better solutions, we needed to really take different solving tools from different areas. There are, of course, a lot of challenges still there. We still have often domain-specific solutions. So, for example, this area of hyperheuristics or general solvers and so on are going in this direction that you can solve any problem if you have the modeling. But often to reach this optimum, you need still to make domain-specific solutions. I'm surprised also myself sometimes that there are still more large and large problem coming. So sometimes you think those are the instances you can have it all in practice, but then you are surprised from much larger instances. And there is, of course, a lot of potential here, especially with the new developments in AI and so on, to deal with these challenges we have here. And regarding machine learning and this project, Appetite project, of course, the data were very important. A lot of time is taken to collect the data, pre-processes them, and so on. And this is also, of course, one of the obstacles why those kind of solutions are not used always in practice. Okay, yeah, this was my presentation. So, of course, this work I'm presenting here is done by many PhDs and postdocs in my lab, and with a lot of colleagues also internationally. And I have listed here most of the references which I have used for this presentation. So if you're interested, you can have a look on those. Thank you very much.
Nysret, thank you very much. Kind of presenting the wealth of the whole work in 50 minutes. I will see if there will be questions from the audience, but just to make the icebreaker question. I think through all your presentation, I thought that one of the crucial kind of problems in applying all these techniques is really the encoding of the problem domain. How do you teach this to your students? How do you teach how they encode the problem? Because I think there, depending on the encoding, it will be easier or less easy to find the solutions, or to speed up in finding the solutions.
Mm-hmm. Yeah, so there are, of course, different ways to encode the problems regarding the technologies, I will say. For example, you can encode it into a SAT problem, you can encode it to a CP formulation, MIP formulation, and so on. And yeah, this is often based, of course, in the experience. So if we understand very well the problem definition, the mathematical definition, then we need also to know, of course, what is available from point of view of global constraints and different encoding possibilities you can use there. But often is, of course, problem specific. So it's kind of solving a problem always for the first time. So you cannot, if I get a new problem, I cannot directly say you can use this encoding or this encoding. Of course, there exist different encodings for different kind of problems, and they can serve as inspiration. But yeah, my course, for example, problem solving and search in AI is often oriented a lot also in case studies, where we take a case studies and we look in different aspects. Where should we use global constraints? Where are the symmetries important? Which variants? So let's say we take first the 8 queens problem and see that there exists at least 3-4 variants to model the problem, to encode it, and then the students manage to to have different different solution methods for different kind of problems.
There's a question in the chat. When comparing machine learning methods to other optimizers, are training time and similar resources factored into the performance?
Yeah, it's a very good question. So it's I was just 2 weeks ago in Dutch seminar about machine learning augmented combinatorial optimization. And there exist approaches now which with GNNs, graph neural networks and so on, can solve some problems like graph coloring and pretty well. But of course, you need to train them a lot. So it's in principle, if you have a good model in machine learning, it will solve the problem faster because it's just based on a prediction, and in some cases. Yeah, this training times is not really calculated there. Good point is, of course, if you have such solvers, is that yeah, you may solve some of the problems faster in some cases. But for complex problems, those approaches are still not working. So it's of course a lot of research in this direction, and yeah, the dean just mentioned now the cluster of excellence, where the idea is actually to join these areas of symbolic AI and sub-symbolic AI, so that You don't use only this end-to-end machine learning approaches, but include also different methods from symbolic AI, which yeah, maybe much more robust than just taking one array alone. Yeah. I think there is also another question which was before about the employee. It is also important for better compensation to employees. It is very important workplace where services are required 24. Yes, so it's very important. Yeah, especially when there's a work in shifts, but also in the organization where, like I mentioned, air traffic control and so on, where you really need a lot of breaks because yeah, there can be problems with the concentrations. You need also these good shifts also in companies where to avoid accidents and so on. So those are important points. Okay, should I read or?
Yeah, perhaps, yeah, or you can immediately answer. We
Yeah.
can all read.
Yes, so those methods, for those methods, yes, we need a lot of data. So usually we have for several years the data, and you need, of course, it's kind of time series predictions. More data you have, better results. Um, um, Coming from different sources. Well, of course we concentrate here in So I mean, it's clear we concentrate here in a specific product and specific, let's say, supermarket. Okay, so we are not developing no models which can. I mean, of course, the models can be used for different tasks, but we train them in specific settings, and then you can use. So it's you cannot use the model you trained for one product to another model directly, but you need really for different products to learn different models to be able to make predictions. Like I know if you make prediction for milk is something else than if you make predicts for other products. But the machine learning models are the same, but the model you apply for prediction may be different. Yeah.
I would have one question more about the synthetic data. You were mentioning that you are also creating the synthetic data, but perhaps I missed this information. How do you know that you have the right synthetic data, so that it makes sense in this for learning?
Yes. So yeah, we generate actually synthetic data more in optimization for optimization problems. We have not generated yet for
For
learning.
learning.
Regarding optimization problems, we especially use this instance space analysis, which so if we have some let's say some real life examples like the blue ones here, when we generate the synthetic data, they should cover them, but also have covered much better the instance space in general. So here we use different features to characterize the instances, and then this tool which we use for instance space then projects them in 2 dimensions with PCAs and on the other methods, and we can yeah, see which features are important, and then of course we can also by changing the values of those features manage to generate even more diverse instances. So we are interested more for diversity and hard instances in the optimization domain. And regarding machine learning, I'm not expert on that, but I think this is also a very hard problem to generate synthetic data there. Yeah.
I would have, if there's none, I would have a last question. You were also mentioning the crossover operators as for this evolutionary algorithms, and that is kind of also difficult to define, when I remember correctly. My question would be, how do you define the crossover operators? How do you know which one makes sense and
Yeah. Yeah, this is also a more art than kind of
experience? Yeah, okay.
yes, it's kind of yeah.
You're playing God.
Yeah.
Huh?
You are taking the problem and have a look where I can decompose it so that I take one part from one problem and another part and join them together. But there are, of course, difficulties sometimes that you may get a completely illegal solution. For example, if you take two routes of traveling salesman problem, and then just join first part and second part, you may have one city twice, and you need then to make a repair there. And usually, sometimes you have a very intuitive operators, and sometimes this may be a more difficult process. And finding those crossover operators is yeah, it's pretty hard. But yeah, in general, I think this is more experience based in general. Yeah, and I think there is another question here too. Are there issues with sharing more specific optimization between companies while avoiding leaking sensitive information? Well, for example, in CD Lab, we do, it's again not contractual research, we do application-oriented basic research. So, of course, we cannot always publish the data of the companies, and this is those are very important for our research because they really boost our methods and so on, and we can find better methods. But we usually publish all the methods, and they are publicly available for all companies so that they can be used. And of course, I mean, some companies, other companies may use them too. So, but we cannot share, of course, every sensitive information from every company. This is not possible.
So since I don't see any further question and we are also kind of running out of time, Nysret, I once more want to thank you. Very insightful presentation. Thank you for sharing your knowledge. I think it's quite an important topic in this area of, computational sustainability. Thank you to all the participants for joining our presentation. I hope to see you next week again, and yeah, have a good evening. Goodbye.
Thank you too. Thank you very much.
Thank you, Nysret.